right? So you have answered the question, if a material is a strong, will its toughness be high? You cannot say. This brittle material is very strong, its strength is high, but it is brittle, so it does not deform too much, so the area under the curve is small. This blue material, the ductile one, is also pretty good in strength, but its toughness is high. Okay? Let us see something else now. I am just showing you lots of different types of steels and so on, or other materials: cast iron, brass, copper, aluminum alloy, annealed copper, and so on. Now, tell me about hardness. Tell me about hardness, right? Or the brittleness. We have just showed you in the previous slide that one material, for example, if it is like this and the curve finishes here, then this material is brittle, right? If I take this material, it goes there and then the curve finishes, then it is brittle, right? So brittle means that it does not go all the way like this. This large deformation, which is the plastic deformation, is not there. At the end of the region, elastic region, it breaks, right? This, for example, yes, is a very good example directly of a brittle material. Okay? But a material like this, it goes like this and ends here, is brittle. A material like this goes here, ends here, is brittle. This is brittle. So they are all brittle if the curve finishes just after the elastic region. But in terms of strength, this is low strength, this is higher strength, this is higher strength, this is even higher strength. Okay? So brittle can be of low strength, brittle can be of high strength. Similarly, ductile, you see all these ductile curves. The ductility of this is very high. The ductility of this is very high because it deforms until here. The ductility of this and this is much lower than this one. Okay? So ductility, but again, this is very ductile but low strength. This is less ductile, right? It finishes only here compared to here. This is less ductile, but its strength is higher. So strength is not related to ductility. Okay? Strength and hardness can be low or high. If strength is high, hardness is high. If strength is low, hardness is low. This is one thing. But if it is very strong, you can't tell whether it has good ductility or not. A brittle material of very high strength can have very low ductility, right? So this should be now very clear. So now you go back, right? Now you have defined all these things. You have defined hardness, you have defined toughness and all the things. You have defined when a material is brittle or ductile. And you have answered, if a material is strong, will its hardness be low or high? Yes, hardness will be also high if its strength is high. How can you experimentally determine the toughness of a material? What are your answers? You can do a stress strain test, right? Normal tensile test, and find the toughness as the area under the curve experimentally. What is the other method? Yes, you can do a Sharpie impact test and you can find the impact toughness of the material. To find the true toughness of a material, is there a test? Maybe you don't know right now. If a material is strong, will it fracture easily? Tell me. If a material is hard, will it fracture easily? If a material is hard or strong, will its toughness be high? Right? Now you know the answers. Let me see if you are very clear. If a material is strong, right? This material has a high strength, but it stops here. I'm not talking of the whole curve. It is a brittle material of good strength. It goes here and stops here. So its strength is high. Will it fracture easily? Okay. Now the same curve, if you go now, this is the second material. So you go here, at this point it fractures if it was a brittle material. If it is a ductile material, it fractures here. So strength wise, they are high strength. Which fractures more easily, right? So you see, your answer is find its toughness. To answer this, find its toughness. If the toughness is big, it has more resistance to fracture. Okay? Right? So if a material is strong, will it fracture easily? If a material is hard, will it fracture easily? So the thing is that if the curve finishes here, it is a strong material, but the toughness is only the area under here. If it goes all the way here, the toughness is all the area here. So the mixed answer is now there. If a material is strong, will its toughness be high? It depends if it is brittle or ductile. If a material has high strength and it is good ductility also, then it has a large area under the curve. So its toughness will be higher. Any material whose toughness is higher is difficult to fracture. Any material whose toughness is lower is easier to fracture. So you should have a combination of the answers. So you see, we have not traveled into the fracture toughness definitions that we wanted to have, but the answer to your short homework 3 was very important. And now you can proceed further. So now we go back, right? We have taken a long time, right? More than half the lecture in trying to revise your previous material science. So if you were very good in material science, very good means not that you had a good grade or not. That is one part. Yes, if your grade was high, if you had a B plus or an A minus or an A, you were most probably good. But was your mind open? Were you questioning your teacher all the time? Were you thinking? So now we are revising some of that with more light, right? The bulb is on. Okay. So we have already done this, right? Stress intensity, this equation we introduced last time, but we talked a little about it. We said that this is a stress intensity K, Y is some factor, sigma is the applied stress, pi is pi, A is the crack length. So stress intensity at the crack tip, this stress intensity at the crack tip, it is dependent on the applied stress, it is dependent on the crack size, and it is dependent on the geometry of the crack, right? Whether it is an edge crack, whether it is a center crack, whether the crack is elliptical in nature, whether the crack is circular in nature, all those things come inside this crack size and crack geometry. The stress intensity factor K1 is used to express the combined effect of stress at the crack tip, the crack size and the crack geometry. Instead of K1, if I say KT, remember, stress concentration factor, then it does not define all these things. It is just a ratio of sigma m to sigma naught. Remember, KT was a ratio of sigma m to sigma naught. If you can find experimentally the maximum stress at the crack tip, and of course you know the remote stress F divided by A, sigma naught. So then that ratio was a stress concentration factor. That we used a few stress concentration factors in machine design. But now the stress intensity is a combination of the applied stress and the crack size and geometry. Sigma is the applied nominal stress, the sigma naught. A is the length of the edge crack or half length of the internal through crack. Y is a dimensionless constant representing the crack geometry. It is the edge crack or a center crack and so on. So now the crack size is also there and the crack geometry effect is also there. Okay, and this is the stress intensity. So this equation, as I told you in the last lecture, is a new equation. This is not from any of your previous courses. This is a fracture mechanics equation. So now after this fracture mechanics equation, can you give a new definition of fracture toughness? So yes, it is the definition. critical value of stress intensity factor is called fracture toughness of the material, right? K1 without this C, K1 was Y sigma pi A, Y sigma pi A. But is there a critical value of stress intensity? Critical value of stress intensity, right? You have a crack and you are applying some load. So there is a stress concentration at the crack tip. Will the material fracture? No, it still does not fracture. You increase the applied stress. This crack grows a little bit. So the stress intensity at the crack also grows. The K1 becomes larger. Does it still crack? No, it is still not cracking. You increase the applied stress further. Then the stress intensity goes further and the crack grows a little more. Does it still crack? Yes, suddenly it goes to crack. So you kept on increasing the stress intensity K1, and after a certain critical value, it will suddenly crack. So that critical value of stress intensity is the fracture toughness of the material. Fracture toughness of the material. So let us read again. Critical value of stress intensity factor that causes failure of the plate under mode 1 loading is called fracture toughness K1C, and it is a material property. Only K1 is the stress intensity under mode 1 loading. K1C is that critical value. So to find K1C, the sigma, the applied load, has become the fracture load, and the crack size has become the critical crack size, right? There was an applied load and there was a crack. So you found the K1 at the crack tip. You increased the load, increased the applied load, so sigma increased, and because of that the crack grew to a new size, so the crack size also changed. With this new value of sigma and this new value of A, the crack size, the K1 increased. You kept on doing this until a critical point reached. Once the critical point reached, the material will suddenly fracture. So the sigma has reached a failure point, sigma F, and the A, the crack size, has increased to a critical crack size. So therefore the sigma is a sigma F and the A is an AC. Sigma F is the applied fracture stress, sigma max in the case, right? And AC is the critical crack length at failure of the edge crack or the half length. Okay. So now if you see what are the units, Y is just a constant, sigma is megapascal, right? And A is the crack size, so it is meters or millimeters or something, right? So this is megapascal, this is root of meter, so that is the unit, megapascal root meter in SI unit, or kilo PSI root inch in the US units, isn't it? So if you are using the SI units, then the unit for this new property called fracture toughness, K1C, is megapascal root meter, and in the British units, earlier British units, now the US units, it is KSI root inch, and here in this table we have this basic material properties, the K1C value and the yield strength. In both units, in the SI units, in the inch pound system unit, different types of aluminum alloys, titanium alloy, different types of alloy steels, So this table we will use quite often for your examples and so on, but this table gives you two very critical properties, the yield strength, which is the end of the elastic region, and the fracture toughness. Now we have not told you how we calculate the fracture toughness, just that if we can measure it, then this is it.